I'm Dr. Joyce Sherpa, and this is Chemistry 222 at Mount Hood Community College. And I figured my very first introduction to you should be in front of what this chemistry is about, which is the transformation of the elements. And this term, the first half of the term, we're going to be exploring chemical bonding. There's two types of chemical bonds, ionic and covalent, that we have explored in 221. We're going to be spending most of our time with covalent. Ionic was a metal and a non-metal, so something from each side of the periodic table. Covalent is when we deal just with non-metals, and they're going to be sharing electrons. And we're going to learn this week how to draw these molecules, drawing Lewis structures. So we're going to do a quick review of some basics. And the first thing to be able to do Lewis structures is we need to know what valence electrons are and how to count them. And the other reason I was standing here in front of the periodic table is to remind you, you all are going to need one in front of you. And so if you had my class last term, you should have your hot pink one. And if you come from another class, you hopefully have one, or you just will have to pull one up on your screen. So I use the periodic table I gave out to you because it has the A numbering in the families, which is an older way of numbering, but it works great for when we do chemical bonding. And so carbon is a 4A, carbon and silicon's family, and that's because they have 4 valence electrons. So we're going to see carbon makes 4 bonds. Nitrogen is a 5A, so it has 5 valence electrons. Oxygen is a 6A, so oxygen, sulfur, selenium, tellurium, and then the halogens, 7A. And where we're all trying to get to is nirvana, perfection, the noble gases that are not reactive. One more that I want to mention, which is number 1, hydrogen. Hydrogen does make a covalent bond when it bonds to our nonmetals. Hydrogen is element number 1. It has 1 valence electron. It has 1 electron, period. All right, so let's flip this and let's do our lesson. Do you like how I flip that? And if you have notes, I posted notes for you, and I will be every week on my MHCC. Let me move this out. All right, there we go. So if you have a printer and the capacity to print these, then you can just follow along and fill them out. If you don't have them, you know, in all honesty, the first 15 years that I taught, I didn't have, my students just had to use notes. So you'll just be writing more, and you can always stop me. Something you couldn't do before. All right. Let's talk about the Octet Rule. That has to do with the noble gases that I just pointed out. The noble gases have 8 valence electrons. So the Octet Rule is that 8 valence electrons is stable. It makes for a very happy atom. They're in heaven. They're satisfied. They've got their octet. The 8 comes from their S's and P's are full. So they have 2 in their S's and 6 in their P's. You should learn about that in 221. If you remember it, great, but that's why it's 8. Oh, the Octet Rule is for carbon. We are carbon-based beings, and carbon wants to be an octet, as does nitrogen, oxygen, and fluorine. There are more exceptions to the Octet Rule than there are ones that obey it. We're going to try and obey it, but we're going to run into the exceptions. So I want to mention those exceptions. So some of the exceptions. Turns out a lot of the elements can have more than 8. And which ones can have more than 8? Well, anything that is in the 3rd row or period, periodic table, and beyond. Which is everything from silicon on, aluminum on, I guess, silicon on, they can have an expanded octet. That's what we call it. Beyond 8 is called an expanded octet. You'll hear me use those terms. That's pretty much the whole periodic table. They can do that because they have d orbitals available. Now you might be going, phosphorus, sulfur, they don't have d orbitals. They are available. They're not using them, but they're there, and so they can expand into them. All right, another exception is fewer than 8. Well, that's everything before carbon. Boron is our big exception here. Boron can only get to 8 with help from its friends. So usually it only goes to 6 electrons. It can get to 8 if it makes a coordinate covalent bond, a special type of bond. But usually it only gets to 6, and it just stays there. It's satisfied. That's it. It's a good lesson for life, that sometimes you go with what you got. All right, another big exception is hydrogen. Hydrogen, remember, only had 1 electron. Its octet is 2 because that makes it like helium. Helium, it's noble gas. So the octet rule is that it becomes like a noble gas. Well, except with these exceptions. All right, and then there's another one, odd number. If you get an odd number, oh, you become a free radical. And a free radical is going to cause chaos in your body. It is the cause of disease. One of the things cause free radicals. So smoking, the best thing you can do for yourself if you're a smoker right now is stop smoking. Your lungs are so important. Your lungs will be so grateful to you. Oh, and if you eat this is guaranteed to cause free radicals. What you can do with it is make a bonfire and like just sing Kumbaya or something, I guess. Oh, and this is when my stepson lived with me. This is like bacon grease from 1 week. This is really gross. Yeah, so be like gnomes. The gnomes, keep it real. Eat broccoli. All right. Eat real food. You can take the challenge. I always offer a healthy food challenge. Make a change. Keep it real for a month. Write about the change you made. Cut out sugar. And get extra credit points. So you just do it for a month. And you type up a little page to me in an email and tell me what you did. In my other class, everyone does it. This class, somebody's going to do it for me this term. All right. Odd number makes a free radical. You have an unpaired electron, and it just causes havoc in your body. Actually, probably the biggest cause in our society is stress. Stress creates free radicals in our body, and it's not good. We want to keep our immune system healthy these days. You know what's something that combats it? Well, they always talk about broccoli and antioxidants. Whole food does it better than any pill does. But love, gratitude, that's going to make everybody happy. And in fact, I'll offer you guys an extra credit. Can't remember if I told you already. If you meditate 10 minutes a day for the month, sending out love, instead of doing all about yourself, sending love to this planet right now, that we all need that. All right, let's move on. Electronegativity. So electronegativity is how we're going to get to this polar, nonpolar. Electronegativity is a greed for electrons. So the greediest thing on the periodic table, does anybody remember? I did talk about this with my class when we did oxidation reduction. Well, the greediest one is fluorine. And so if we flip back, can you see it? Yeah, that corner over there, fluorine. Fluorine has the greatest attraction for electrons. And as you move towards fluorine, become more and more electronegative. Okay, sorry, it's the only day I'll do that probably, unless I decide I really like it. So as far as electronegativity, I'll write it under here. We're going to polar in a moment. Electronegativity I don't have you guys here to correct my spelling. I don't have you to correct my mistakes. I make mistakes. I am human, in case you can't tell that. So electronegativity is their greed for electrons. Fluorine is the most, because it's one step away from being like neon, and so it's really greedy. Oxygen is number 2. So if you did print the notes, or even if you pull them up, I did post the electronegativity table that Linus Pauling came up with. There's a new one that's out there that I'm kind of a Linus Pauling #1 fan, so I stick with his table. He made up these numbers. Fluorine, he assigned it a 4. Gave it, you don't have to remember this. Oxygen, he said, okay, it's a 3.5. Nitrogen, he said it's a 3.0, etc., etc. And then based on the difference in their electronegativity, we could determine if something was polar or not. Now, before I go on, it is also really easy to remember these three because they spell NOF. Put a little G in front of it, that spells NOF, which is the hat that gnomes wear. So I have a rainbow NOF. So keep it on. NOF. The gnomes are really helpful. Listen to the gnomes. So nitrogen, oxygen, fluorine are the greediest. Fluorine the most. And you see those, you're going to have something that's polar. The word polar means pull. It means a pull. So looking at our examples, sodium and fluoride actually made what was called an ionic bond. In this case, the electrons can be completely transferred all the way over to the fluorine. So you have a positive and a negative. And we can recognize that because they're from two different sides of the periodic table, metal and non-metal. But what we're going to be looking at is covalent bonds. There are two types. There are polar ones in which something is pulling, like here, fluorine is pulling. And the way you show that is you show an arrow towards the fluorine saying it's pulling the electrons. And you put a little positive on the carbon. So we say the fluorine is more electronegative, it's pulling the electrons, making the carbon electropositive. It hasn't made a full positive and negative, it's just an area of positivity and an area of negativity. So it's like 4-year-olds. Mom says, hey, you have to share. And the 4-year-old's like, okay, I'll share as long as the toys stay closer to me. And that's what fluorine does pretty much all the time. When it doesn't, it makes something called a non-polar bond. So carbon-carbon is an example of non-polar, which means there's no pull. It makes sense. Anything to itself is not going to pull. It's going to be an equal distribution. So fluorine, the only time it does not make a polar bond, the polar bear here, he's looking, the only time it's not polar, well, not, is when it binds to itself. So for nonpolar, what you need to remember is something to itself is nonpolar, and carbon-hydrogen is nonpolar. You're going to see me just write NP for nonpolar. That was where his definition, Linus Pauling's definition for nonpolar came from. He knew that things that are made up of carbon and hydrogen do not mix with water. So another term for nonpolar is we often use that things are hydrophobic. So they don't like water. In biology, because we are water-based, they use the term hydrophobic. But there are things other than just water-based that are non-polar. And carbon-nitrogen, the definition for polar was an electronegativity difference greater between X is our symbol for electronegativity. So if the difference is more than 0.4, but less than 1.9, he said it was a polar bond. So sodium fluoride, it was more, so it's ionic. Carbon-hydrogen was less, it was 0.4, so he said it was nonpolar. So that would mean you're gonna have to keep looking at that chart. Do you have to memorize the chart? Oh, this first half of the term, it's all open book. So you're gonna have this chart. You pull the chart up. But in all honesty, you don't really need to look at the chart except for some of these examples and maybe the first homework set, you might have an example. If you see something to itself, you know it's nonpolar. If you see metal, non-metal, you know it's ionic. Carbon, hydrogen, you need to remember that. Next week's lab is organic chemistry, and so at that point we'll get driven home. And then usually when you see two different things, especially if you see N, O, or F to anything, NOF, the nose hat, you guys should all learn how to crochet or knit a NOF. Maybe we should do that as an extra credit. You can show me in the virtual office hours, which are going to be mandatory. Not every single one, but once a week, you at least have to stop in for 10 minutes so I can see how it's going. It's a good contact. All right. Carbon, nitrogen, also polar. So both of these are polar. And that would be how you can show polarity. You would not do those arrows with the first two because they are not polar, there's nothing pulling. And with the last one, you also would not because there's a full transfer. All right, the question actually asked, which of these is the most polar? Oh, it looks like it's right from a multiple choice test. I have not figured out how I'm going to do your test. It will be at home for the first test, and it'll probably be also your work, because why not? Carbon and fluorine. The further they are apart on the periodic table, the greater the difference will be, the more the pool will be. All right, on question number 2, we're going to show polarity. Now, we first have to know if there is a pool, and I had to retape this, but I found my knot, so it was worth it. I forgot to look at the chart, which was right in front of me, and it turns out, if you look at chlorine and bromine, chlorine on the electronegativity scale gets a 3.0, and bromine gets a 2.8. Turns out, they're nonpolar. There's no pool. So we wouldn't show it. I avoid that one, because your teacher got it wrong and has to re-videotape herself. All right. Now, aluminum sulfur. If this was a question on a test and you said it's ionic, I would give you credit, because that's what I would assume it is. If we again look at the chart, this question is to just show you how the chart works. And for people, because there's always somebody in here who has become inspired, maybe a lot of you have, because you guys are the change. We need changes out there right now. And so you might want to go into chemistry. And when you take a higher level chemistry, they will refine this. They will probably have the new chart. By the way, I'm wearing rose-colored glasses so that everything looks like roses. You guys look beautiful. This is really funky, teaching in front of a room that, well, I have a couple stuffed animals in here, so I didn't feel completely alone. But anyway, I imagine you're all in here. And this is not our classroom. This is the classroom we're supposed to be in. And it's a beautiful classroom. It has 8 blackboards. All right, this difference is 1.0. It is in this range of polar. So we can show it. We can show it with the arrow like I did above. I'm going to show this one a little bit different. I don't care which way you show polarity. What I need is that you recognize, so when I do it, you don't go, what is she doing? You still will probably do that. All right. You can make these funky. It's a delta. It's like this loopy round D. So it's fluid and a negative. In biological sciences, they often use those signs. So it shows the area of negativity and the area of positivity. Again, the way I taught my class, metal, non-metal, we're going to go with ionic. Those of you who want to go to a higher level, you can refine some of these details. All right, bromine and sulfur. Again, it's not what I just started. Bromine is 2.8 and sulfur is 2.5. So that is considered a difference on Linus Pauling's chart. Again, if you're going to go to a higher level, use the new chart. Unless you want to be like me and just say, no, it's all about Linus. All right, so that one would be nonpolar. So on your homework, on a test situation, realize you have your chart and this is the difference. And I usually avoid ones like that because it's so tedious to keep looking at this chart. All right, oxygen and nitrogen. We have enough. We're going to have polar. I am a biochemist. So I am all about carbon, nitrogen, and oxygen, which doesn't really spell a word. That would be sn. I don't know. Maybe that's the language the other gnomes from the other planet, the other dimension speak. So we can show it with the arrow. Oxygen's always going to be the one pooling. Oh, there's one exception to that. When is oxygen not going to be pooling? Actually, there's 2. If it's with itself, take a deep, glorious breath. I heard a video that's like breathing is so important. Keeping your immune system healthy. Keep your immune system healthy. Eat healthy. Get fresh air. Breathe. Breathe slowly and enjoy. And yeah, because we're all in this together. All right. You can show it with the delta, and oxygen is always going to be pooling, except with itself or with fluorine, because fluorine is the greediest thing up there. All right, hydrogen is going to make a polar bond. I guess I better look. Oh yeah, 2.1 and 2.8. So this is polar. Again, I'm going to make them polar or definitely non-polar, carbon, 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 hydrogen. This question was more to show you the nuances of that table. Hydrogen doesn't ever pool. It has 1 electron. it's willing actually to give that one up. And so we show the pool. This is an acid. It is a very polar covalent bond. And that's what's special about acids. So you can show it that way, or you can show the deltas. And you'll see me using both ways. So those last two are definitely polar. All right, we're going to classify for the last thing on this page. Chlorine Fluorine. Oh, well, anything of fluorine is polar. So this is definitely polar. Phosphorus to hydrogen. I honestly have to look it up. Oh, they're both 2.1. So this is non-polar. Again, a nuance of the periodic table. I avoid all those little nuances, but yeah, something we should watch for. Carbon, hydrogen, you need to know that is non-polar. Calcium, oxygen, two different sides in the periodic table. We can look at our table. It's a 1 to a 3, so the difference is very large. So we would get a +2 and a -2. This is ionic. And so polar and non-polar do imply covalent, so you can just say polar, non-polar. Ionic means we've gone beyond covalent. The transfer has happened. I want to do one more thing, and that is I'm going to show the polarity. So again, you can show it with the arrow. Fluorine is always going to be pooling because it is the greeniest thing. It's like the little top of our knoth. Or we can show it with those symbols. So chlorine gets the positive. They're just fun to write, these little fluid delta signs. And so it stands for dipole. So the D is for a dipole, which means there's polarity. It's a verb, I'm sorry, an adjective. Polar is an adjective. Dipole would be noun, and they mean virtually the same thing. For our purposes, they do. All right.